Hi everyone. In this session I'm looking at measures of relative location, and to see exactly what that means we'll start off with an example in a moment, but first just look at the outcomes quickly. Very important, know all the definitions, the purpose of these summaries, which method is best for which type of data, how to calculate them, and extracting information. Now the actual calculation of these numerical summaries is not that important. It is secondary to knowing the definitions and extracting information, and the reason is because the calculation is done using software such as Excel. Right, let's start and look at an example. Now consider the following exam results for a class of 30 students. This is the dot plot that was discussed in another session, and these exam results range from low 20s up to the low 80s. Now your result that you got for this exam is 64%, and this is where you are sitting at. Now the class average for this exam is 50%, and if we look at the rest of the results, then there's only 3 results better than yours. So only 3 other people beat you in class, you with your 64 and the class average being 50. So if we compare your result to the others, then your result is actually quite good, because there's only 3 people who got more than you who got 64. Okay, all the others at a class of 30, that means 26 others got below you. If we look at a different situation where we still have the 30 students with their exam results and you still have 64, but now the class average is sitting at 82. That means basically the entire class performed better than you with your 64. It means that your result compared to the others is actually really bad. So although it's still the same result, 64, if we compare it to the class average initially, which is 50, then it's good. If we compare it to the others, then it's good. However, if the class average is 82 and you still have 64, then comparing you to the class average suddenly doesn't look that good. And comparing to the others also doesn't look that good either. So in this session we're going to be looking at relative location. So not just where you are, which was the measures of location, like the average, but where you are in relation to the others and where you are in relation to the class average. Where you are in relation to the others will fall under the section of quantiles or percentiles, and where you are in relation to the class average will be under z-scores. Right, so how do we calculate this relation? Now, relative position, we can refer to those as quantiles, and we'll get into the details in a moment. The relative spread or dispersion will be things like the range, interquartile range, and z-scores. Right, now the z-scores can also be under relative location because it tells you something about your position, but it also tells you something about the distance of your position. Right, so first of all, quantiles. Now a single quantile divides the data set up into 2 parts. Don't think of it as equal parts, it just divides it up into 2 parts, and we'll see how in the examples. In order for this to happen, the data must be arranged in ascending order. So the first place where we saw this was with the median. And the reason for that is because the median is a special quantile. The median divides the data set up into 2 equal parts. Okay, where generally quantiles don't do that. It's just the median that divides the data set up into 2 equal parts, but the data set must be arranged. Now quantiles can be subdivided into 3: quartiles, deciles, and percentiles. Now the 2 most common ones will be quartiles and percentiles. The deciles are not that common. The percentiles we can think of as a generalized version, because it really covers the deciles and the quartiles as well. So percentiles is a bit more comprehensive, and you might as well just work with percentiles to start off with and ignore the others. Right, now quartiles divide our data set up. How does it divide it? Well, into quarters, like the name says. The third quartile, as I've indicated here, means that 3/4 of the data, or 75% of the data, must be less than or equal to this Q3 value. So obviously if we're looking at Q2, then it means that 2/4 of the data must be less than or equal to Q2. And Q1 means that 1/4 of the data, or 25% of the data, must be less than or equal to Q1. So Q1, Q2, and Q3 will be the actual values that we represent, or that we identify on the x-axis, and those values will divide the data set. Q1 separates the lowest 25%, Q2 the lowest 50%, and Q3 the lowest 75%. Deciles is exactly what the name says. If we look at the third decile, then 3/10 or 30% of the data must be less than or equal to whatever this decile value is, D3. So obviously if we look at D1, then 10% of the data must be less than or equal to D1. D2, 20% of the data, all the way up to D9, 90%. So D9 will be a value that if we put it on the x-axis, we will have 90% of the data less than or equal to whatever this value is. And if you think of the way in which this is done, it's accumulating Q1, Q2, Q3, 25, 50, 75%, D1, D2, D3 up to D9, that's 10%, 20%, 30% up to 90%, then you should be thinking of an ogive. Right, and then lastly, percentiles, exactly what the name says, percentages. So there's 99 percentiles, and if we take, for example, P98, P98, then it means that if we indicate P98 on the x-axis with our data, then 98% of the data will be less than or equal to P98. Now, in order to determine percentiles, we have two steps. The first of all, we need to find the position of the percentile, decile, or quartile. So we'll just call it a quantile. We need to find its position, and then we need to determine the actual quantile value. Now in Excel, there's a function that we can just enter. We highlight the entire data set, and we type in percentile, and it will give us the percentile value if we specify which one we want. Right, but for our purposes at this stage, let's just look at it step by step. So important, two steps. We need firstly to find the position of the quantile, and then we need to determine the actual quantile value, because it's just indicated by these letters over here. We don't know what the values are. That will depend on the type of data set that we have. So first of all, let's go back to the data set that I've been working with all along. We have raw data. So as they were observed, they were recorded. Capital X refers to the whole thing, right? All the observations. Lowercase x1 refers to the first value in the data set. Lowercase x2 the second, all the way up to x20. And the y's, y1 to y20, remember that is ascending data. Okay, we also refer to this as ordered values or ordered statistics. Now that is what we need in order to find our quantiles. We first need to arrange the values in ascending order. Now when we construct a dot plot for the data, it automatically is arranged in ascending order. Over here, I just ranked the observations. Okay, these are the ranks. So 0 will have the first rank, which is 1. 70 will have the second rank, which is 2. It just indicates the order in which they appear from smallest to largest. Right, so let's start with the quartiles. If I'm interested in calculating Q3, then remember 75% of the data. So the first step will be to find the position of Q3. And there's a standard formula for that. We'll take 3/4 and we'll multiply it by the size of the data set plus 1. In other words, the size of the data set plus 1 will be n plus 1. So we'll take 3/4 times n plus 1. Now where does the 3/4 come from? The 4 will be the number of quarters because we're working with quartiles, and 3 will tell us which quarter we are interested in. And it's the subscript of Q3, so that's what we will use. So that means we will take 3/4 of 20 plus 1, and that gives us 15.75. Now if we look at our data set, we don't have a 15.75 position. we have a position 15 and we have a position 16. So that means that our Q3 position lies between Y15 and Y16. And where in between those two? Well, if we take only this part and treat it as a percentage, then we can say that our Q3 position is 75% past Y15. Because we're not sitting at 15, we're not sitting at 16 either. We're sitting in between the two, and we're sitting at 75% past the 15th position. So we need to take 75% of Y16 minus Y15, and we need to add it to whatever Y15 is. And that's exactly the calculation. So the first one was the position, and now we calculate the actual value. So we'll take whatever Y15 is because of this position, and then we will take 75% of the difference between Y16 and Y15, and that is where the 75% comes from. So looking at the values that we have, Y15 is 220, Y16 is 230, so we'll substitute 220 in here. There we'll have 230 minus 220, and we'll take 75% of that. So that means 75% of this, okay, 230 minus 220, that's 10, and 75% of 10, that's 7.5. So we'll take 220 plus 7.5, and that gives me my 227.5. So you can see we're not sitting at 220, but we're not sitting at 230 either. We're sitting in between the two at value 227.5. So that means that because it's Q3, that 75% of the data is less than or equal to 227.5. So from the 227.5 in there, all of this down here, that will be 75% of the data. And obviously above it, we will have 25% of the data. Right, let's have a look at Q2. Now the steps stay exactly the same. First the position and then the actual value. The method stays exactly the same. We're interested in the second quartile, so that's 2 out of 4. Still data set plus 1, so that's 20 plus 1, so 2 quarters times 21, that's 10.5. So that means we're sitting at position, okay, at position 10.5. We have no position 10.5, we have a position 10 and a position 11. So that means we'll take whatever we have at position 10 and we'll add 50%. Add 50% of Y11 minus Y10. So if we do that, then we substitute 200, okay, 200 into Y10. Y11 is 200 minus Y10, which is 200. 50% of that, the 50% of 0 is 0, so that just stays 200. Now, that means we're sitting exactly in the middle of the data set. We have 10 values to the left and we have 10 values to the right. So this is in fact the median. 200 is the median. If we recall from our measures of location, when we calculated the median for this data set, we took the average of Y10 and Y11, which is exactly what we did over here as well. Right, what about Q1? So first quarter position, or first quartile position, that means 1 quarter of 21. That gives us 5.25, which is the position. We don't have a 5.25 position, we have a position 5 and we have a position 6. So that means we'll take whatever we have at position 5 and we will add 25% to it. So 25% of Y6 minus Y5. So if we go to our calculation for our Q1, Y5 is equal to 140. That value over there, 140. Then we're not sitting at Y5, we've passed it. Think of this on the number line, we've passed it. Right, we've passed Y5, we're heading on to Y6, but we don't reach Y6. We only reach 25% of the way. The total distance is 10. So if we take 25% of 10, that's 2.5. So 2.5 plus 140, that's 142.5. Now if we combine the three quartiles that we just calculated, the 142.5, the 200, and the 227.5, onto one dot plot, then we can see that 25% of the data in the first part is spread over a much bigger distance than the rest. And the 25% over here is spread over a very small distance compared to the rest. Now 25% represents the number of observations, but this spread over here refers to the distance between them. So looking at this, we see that we have a very high concentration over here and a very low concentration over here. This is important. We'll get back to it just now. Now if we look at deciles, then the calculation steps are exactly the same. The only thing that changes will be the fraction that we're working with. Previously we worked with quarters, now we're working with tenths. So that means if I'm interested in the third decile position, it'll be 3 over 10, still the sample size plus 1. That gives us 3 over 10 times 21, which is 6.3. We don't have a position 6.3, so we'll take position 6 and we'll add 30% to it. 30% of what? Well, 30% past y6. This is where y6 comes from. So y7 minus y6, 30% of that. So here's the calculation. y6 is 150. y7 is 170 minus the y50, which gives us 20. 30% of 20 is 6. So 150 plus 6, and that gives us our 156. So here's 150, there's 170, so there will be 160, so 156 will be about there somewhere. So that is where D3 is. That's the position of D3, and that means 30% of the data is less than or equal to D3, which is 156. And the same for all the other deciles. We simply will change now this value 3 throughout the calculation and adjust the values accordingly. Right, for percentiles, it's exactly the same situation. We just make a change now to 100 because we're working with percentages, 100. But we're still going to get a result for the position which contains a decimal, so it means that we're not sitting at position 12, we're sitting 60% past position 12. Okay, this is percentage. So there's position 12, which is 210. So we'll take whatever we have, which is our 210, and we will add 60% of the difference between y13 and y12. So that's 220 minus 210, that's 10. 60% of 10, that's 6. So we'll add 210 and 6, and that gives us 216. And that is the 60th percentile. So that means in here, we're going to have a value 216, and 60% of the values will be less than or equal to 216. Now when I started this, I mentioned ogive, and here it is. We have the cumulative percentage on the vertical axis, and we have the actual values on the x-axis, the horizontal. So if we're interested in, let's say, Q3, which is the third quartile, which means 75%, so it is just P75, right, the 75th percentile. Then because this is cumulative, right, the ogive is cumulative. So because this is cumulative, if I go across and down onto the horizontal axis, then my cutoff point will be over there. We've calculated it to be 227.5, so that means 75% of the data, which is over here, okay, 75% of the data is less than or equal to 227.5, and the remaining 25% will be over there to the right. In other words, that 25% over there. And the same with the others. The third decile, 30%, so we find it on the vertical axis, we go across, we go down, and that means we have now the cutoff point for the lowest 30% of the data.